In this digital jungle, where packets vanish like dames in the fog, one man's gotta chase the truth. Name's Dr. Jonas. I ain't no hero, just a programmer with a grudge against unresponsive hosts. Yeah, you know the type. The ones that ghost you faster than a bad date. Tonight's case, the elusive ping. That sneaky utility that shouts, "Hey, you alive," into the void. But the stock one's got baggage, bugs, limitations, like a snitch with a loose lip. So I'm building my own from scratch. Raw sockets, ICMP echoes, the works. No shortcuts, no libraries. Just me, the code, and a bottle of coffee. Stick around, kid. We're diving into the shadows of networking. Might get messy, might get funny. But hey, in this line of work, if you can't laugh at a timeout error, you're probably offline. Sup guys, welcome to today's show. So today we are going to try to finish our ping that we have been written from scratch, and we're gonna take care of the function that receives an IP packet. Last time we created the send IP function, and we managed to be able to send a proper ICMP packet. But I discovered a bug. Here I am logged into my box ending in .6. So this is what I want to ping to. So I'll start a TCP dump where I check for ICMP and the host address of 10, like this. This is the IP address of my coding machine. I need to say ICMP and this. So first let's try to send one packet using the regular ping software. And as you can see, we get this ping packet, ICMP echo request, and we get a response, ICMP echo reply. So this is the result we're looking for. But when we run our code, like this, as we can see, it's from this to this. We do get the proper ping, and it looks right every field, but we don't get the ping reply. So that means that this packet must be malformed somehow. Otherwise, my Linux machine would have responded with a ping reply. And after some troubleshooting, I figured out what the problem was. So, do you remember this checksum thing that we coded, which goes through every part of the packet 16 bits at a time and sums it all up? Well, at the end I return the reverse endian of what it currently is. So it becomes big endian from little endian. But since everything of this is already calculated based off big endian, we should not reverse it again. So here we should just return the return value. And if we do it like this and recompile this thing and we rerun it, now we get the proper response. So now we know that our ping works. It sends a correct packet, but what's left is receiving the ping reply, making sure that the connection goes in both directions. So this is the task of today. We are going to implement a function which is going to receive an IP packet. So basically we want to do something like, do you remember the data structures we have? So for instance, we have let's see where it is. Here. We have a ping packet which has all the fields that we find interesting, like the kind and the source and the destination IP addresses and stuff like that. And then we use an eval function to evaluate this into a string containing all of these fields necessary for actually sending an IP packet on the network. Well, now we want to do the reverse. So we want to receive a packet and it's going to be delivered in this format. Then we need to run the checksum algorithm and make sure that it's correct. And then we need to transform this into this data structure so we can present it to us and compare and stuff like that. So let's get on with it. Alright guys, let's do this thing. So let's create the function which receives one IP packet. So let's see where we should put it. Here is our send IP. So I guess we want to return an IP packet. This is going to be called, let's see, send IP, receive IP. And what do we need? Let's see, this in 32, is this, let me just check, send IP. Okay, so that is a raw socket, right? Well, we do need that. So this is a raw socket, and do we need anything else? I don't think so. No. Let's start there anyway. So let's go up here and create this function. So IP receive IP in 32S. And we're gonna need a buffer. So how big does this buffer need to be? Well, we are not going to support jumbo frames, which are IP packets on the size of 9,000 bytes. So the regular MTU, as it's called, maximum transmission unit, is 1500. And then there's some headers and stuff, so maybe 1540 or something. Which means that our buffer can be 1600 and we should have enough room. And we need to have an IP pointer. Let's call this IP packet. IP packet like this. And we also need to have one for the raw IP packet, I guess. Yeah, let's do that. So I'm not sure what I'd call it. Is it raw IP or? Yeah, I guess. So this is the, no, let me double check that. Struct S raw IP. Okay, I never made a specific specific data type from it. So let's say we have a struct s raw IP, and we can call this raw like this. And we need to check that we have an S, otherwise we can return IP 0 like this to indicate an error. Okay, so now we want to receive this packet. By the way, let's zero out our buffer first. So this is going to be the address of buff and 1600 size. And we also need to take care of return values. So let's say we have a sign into ret like this. And ret is going to be equal to receive from is the function we need. And I'm not entirely sure about its parameters, so let's check command to receive from. So the fd buff size, let's start there. So the fd is going to be this s. The buffer, did it show a specific data type for it? Void. Maybe we should cast anyway. So let's say, let's do this. No, that's not. Let's try this first and see what it says. And let's say 1599 as the size. And what else is there? We have flags and source address, and this we don't need because we get all of this from the packet header. Maybe we need some flags, we'll see about that. But otherwise 0, 0, 0, I guess. And what is the return value? Number of bytes received, or -1 on error. So let's see here. Maybe we should have some counter or something. Let's say this is the n, so we can calculate the size of the payload. I don't think that will be specified. Maybe it will though. So if ret is less than 0, we return an error. Otherwise, we can set n equal to the return value. So now we have the size of the entire thing. And the raw IP packet is going to be this payload. So we can set our raw pointer equal to a struct s raw IP star of the address of the buffer, I guess. Okay, and if we want to create one of these IP structures that we have, or that we want to have. This one, I think we have a constructor for that, right? Yes, make IP. Let's check what's needed to make an IP. We need the kind. We need the source and destination addresses. We need an ID. ID, what's that ID? Okay, so that's a global thing. We have a counter which we increase. Do we put that inside of the packet somewhere? Well, we put it here. What about when we evaluate this thing? Do we propagate that ID somewhere? Yeah, we set it inside here. Okay, but then we can easily extract it. That's no problem. And what was the last thing? Okay, so either we specify a specific ID or we give it a pointer to this global thing, right? Let's see how we did it here. It was a little while ago I made this thing. So let's see. Okay, we give it a random value here. But we can set this to 0 and use this instead. And that is what we want in this case, right? Yeah, it is. Okay. So let's try to create this thing. Maybe we can create variables to make this a little bit more explicit. So let's say we have an int 8 source and a destination, and an int 16 ID, and we need to have a kind as well. And what is a kind really? Is it this thing? Yeah, it's a type. So, alright, we need to extract what kind of packet it is, right? So let's say that we have a type with a name kind, like this. And that's probably all we need, right? And we have access to the raw packet here, so let's start by extracting this ID field. So ID is going to be equal to, and we need to endian this thing. And it's going to be the raw IP packet ID, right? So that is our ID, easy as pizza. And our source, let's see, see. It's going to be equal to, we need to make this a string. So we're going to call the bird-shooters function to dotted, which takes an IP address as an integer in network byte order and reverses it and makes a string out of it. So we need to provide the raw packet and then the source field, I guess it's called. Let's see. Yes, source. And we have the ID, and we have the dust. And we need to do the checksum calculation as well, right? Let's see, when we call the, no, this is not right. When we call the checksum function, what do we give it? So in this case we have the eval IP. So we give it the ret and the length little endian. And where do we get the ret from? Ret is equal to p. P is equal to, okay, yeah, okay, so this is the packet that, the string containing the packet that we are dealing with. What about the length in little endian? So if we have a payload, it takes the header size and it adds the payload size. And the ICMP headers. Okay, so it's all of these. Let's also create an int16 checksum like this. Alright, so ID, we have source, and we want to have the destination as well. This is the destination right here. And I guess the checksum can just be calculated by calling the checksum function on our buffer, right? What's the first argument of the checksum? An int 8 star and then a size. So we can give it the buff. And the size, we can give it n, which was returned, because we want to calculate it based on the entire thing. But if it is a, if the size is not divisible by 2, then we're in trouble. I don't remember if the checksum checked for that. No, it does not take that into account. I know that we have checked in other cases, so it still works, but in this case we need to do a check as well. So let's see if the size is divisible by 2. Or if it's not, rather. Let's see. If it's not divisible by 2, we want to increase n. And it won't be a problem since we have 1 extra byte here, plus we have zeroed it out. So this will be a 0 in that case, and the checksum will check out. All right, and then we want to compare this thing. So let's also have a checksum prime. Where the checksum prime is equal to the raw IP, to the endian 16 of the raw IP packet and its checksum field. And then we want to compare these two. Alright, welcome back guys. So now that we have the checksum in the correct format, we can compare the two. So let's see if the supplied, the calculated checksum is equal to but we need to calculate the checksum without, let me see. Right, what we want to do is not comparing the two. So let's remove this one. What we want to do is check if the supplied, our calculation of the checksum, if that is equal to 0xFFFF, then we know it's right. So if it's not equal to that, in that case, let's see, we can print some error message. Something like received packet with malformed checksum. And then we can provide that checksum. So 0x% 04 hx. We'll get it in 4 decimals or 4 digits. And then we provide the integer of checksum. Or rather, the integer of the raw packets checksum. And let's also return an error, like so. Otherwise, it's okay. And now we have all the different parts, so we should be able to create an IP packet by calling make IP. And let's see. By the way, what was the first argument? I can't remember. Make IP. Ah, the kind, that's right. And we have the source, destination, ID, and this. And the kind is one of these enums. Echo, echo reply. No, it's one of these. So if the packet contains an ICMP, a TCP, or a UDP payload. So let's see, which one is it? This one, the protocol. So if that is equal to ICMP, then we can deduce the enum. So how did we do that? If we go to the make IP function here, where do we set the kind? Okay, we just take it like this. So let's see, where do we use make IP? So here we say L4 ICMP. Okay. And when we evaluate the IP, how do we do with this protocol field? I will set it to 1 if it's L4 ICMP. Okay. So let's do the same here. So let's set the kind equal to, if the raw packet and its protocol field is equal to 1, in that case we set this to L4 ICMP. Otherwise we set it to unassigned, or what do we call it? Unassigned with a small u. Like so. And now we can create this thing. So we give it the kind, we give it the source, the destination, the ID, and a 0 at the end. And if we don't get an IP packet back, we can return an error. Or we don't need to do that actually. We can propagate the error, so we just return the IP packet like this. Okay. What about the payload? Source, destination, ID, and this. Where do we have the payload? Packet payload is 0. How did we do the payload? Because here we create the IP packet. Okay, then we set the payload afterwards. All right. And what is the type of the payload? An ICMP. Okay. So we need to do something like this. I guess we should make a copy of the payload. should do something like this. If the kind is not equal to L4 ICMP, then we can say something like unsupported packet type received. And then we can specify the protocol specifically. So we can do that as a 4-digit hexadecimal like before. And this time we take the IP protocol field and return an error, because this is the only thing we support at this point. Otherwise we need to make a copy of the payload, and in order to do that we need to calculate its size. And basically the size of the payload is going to be this n minus the size of the header. So maybe we can do something like let's do this. N is minus equal the size of struct s raw IP. And if this is 0, so there is no payload, then we can be explicit about that and say that the IP packet payload is ICMP 0, and then we return the IP packet. But if we have a payload, we need to make a copy of that, right? And that needs to be this ICMP structure. So we need to extract that as well. So let's create a struct s raw ICMP, and we can call this R ICMP, and we also need to have a regular ICMP packet. So I packet is that. So we need to start with a raw packet. So the what did I call it? R ICMP. So the R ICMP is going to be equal to well, let's just set it to the struct s raw ICMP, and we'll take, let's see, we'll take the address of the buffer plus size of struct s raw IP. Then we should be at the right position. And now we need to do basically the same as we did here, but for the ICMP. So we need to extract the kind, the size, and the data. So let's say that we have a int16 ICMP size, a type ICMP kind, and let's say that we have let's say that we have a struct s ping, which is the ping packet, and that is the payload of this ICMP. So basically this stuff right here. And the data field we need to allocate. So let's say int 8 data. A lot of moving parts, eh? We also need to have a checksum for this thing. So let's say that we have an int16 ICMP checksum. Alright, so let's try to extract those different things. And let's start with the type and the code. So if the RICMP type is equal to 8 and the RICMP code is 0, in that case we have an echo packet. So then we can set ICMP kind equal to echo. Let's double check that. Yes, echo and echo reply. Otherwise, if the RICMP type is 0 and the RICMP code is also 0. I think these are the right ones, but let's double check. So echo is 80, echo reply is 00. So ICMP kind is equal to echo reply. And in all other cases, ICMP kind is equal to unassigned. Yeah. Alright, so that is the kind thing, and the size the size we need to calculate. So currently, what is n equal to? N is equal to the entire layer 4 packet. So we need to remove the ICMP header from it as well. But maybe we can wait a little bit with that. If we check the make ICMP function, it takes both the kind, the data, and the size. And the size is just the size of the payload. Okay, so let's do this then. So we set n minus equals size of struct s raw ICMP. If we don't have anything, ping packet. Then we set ping packet to a 0, but we need to cast it as this structure. Otherwise, we need to allocate for this thing. So in that case, it's going to be equal to mal struct s ping malloc n. But before all that, we also need to check if it's unassigned. So if our ICMP kind is equal to unassigned, we need to mention that this is the wrong kind of type of packet, like before. Unknown ICMP packet received. And then we can print the type and the code. So the R ICMP type and the R ICMP code. In that case, we can return an error, I guess. Otherwise, we check for these. And down here, we can zero out our ping packet. And then we can copy into our ping packet. And we want to copy from the R ICMP data. That's the name, right? Yes. And we want to copy n bytes. So now we have a copy of this payload right here. So now we can take the IP packet and set its payload. This is a payload of the ICMP packet. And we still need to have the raw ICMP packet header as well, right? Or maybe not. It's enough to have this thing. That's right. We can create this with our constructor function now. So let's wait with this thing, and let's set, what do we call the pointer? Ping. Don't we have an ICMP? No. Wait a second. IP packet. This should be IP. No. Maybe I should have a different name for this. ICMP packet. And the IP packet is IP. Okay, now I see. So the ICMP packet is going to be equal to make ICMP. And we take our ICMP kind, we take our ping packet, so we need to cast this as an int 8, and this is the ping packet, and the size is n. If we don't get an ICMP packet, let's just return for now. Let's just return the IP packet without a payload in that case. Otherwise, we can set the IP packet's payload to our ICMP packet. And I think that's all we need in order to receive an IP packet, because now we have it in this form. The payload points to a structure of this form. The data points to either this ping packet or it's empty. I think this should do it. So how can we test this? Well, we have a main where we send a packet. So let's create an IP structure for the received packet. Let's call it reply. And after we have sent this thing, we can actually clean up in between as well. Then we can set our reply equal to receive IP, and we provide our S. If we don't have a reply, we can print an error. Return -1. Otherwise, we can do show of the reply. And then we can free the reply. We should also free the data, right? So let's check if we have ICMP packet data. We will free that data. This is called payload. And if we have a reply payload, we can free the reply payload. And then we can free the actual reply, and we end. Alright, a lot of moving parts. Something tells me that we're gonna need some troubleshooting right here. Argument 1 of 0, incompatible pointer type 25. Okay, we need to cast it like this. Expected expression before IP 51. Okay, so IP is not the name of this thing. IP packet or raw it should be. Statement with no effect. Okay. So if this is 8 and this is 0, or this is 0 and this is 0. How can that be a statement of no effect? Oh, it should be else if. Classic. Expected expression 78. Ping packets, that's right, this should be a 0. Conversion to non-scalar type requested, 78. Right, this should be a pointer. Zero makes pointer from integer 82. So we zero the ping packet. Oh, this should be 1, and same here. And here. Unused variable. Right, we forgot about this one. Data ICMP size. So data, I guess we can remove ICMP size as well. What about the checksum? We should actually do the checksum check on the ICMP packet as well. Let's do it. So the ICMP csum is equal to checksum of well, it's the raw ICMP packet. And I guess we need to cast it like this. But what about the size? Well, we haven't deducted the headers yet. So I guess we can just propagate n here. And what if it's not a multiple of 2? Let's do this. Because I don't want to copy stuff from all different directions right now. So if the ICMP checksum is not equal to 0xFFFF, then we need to produce an error. Here we can give the raw ICMP packets checksum field. Something like that. array subscript 8000, it's outside bounds. Let's offset 32,000 into buff. That can't be right. R ICMP type. Because the R ICMP is a raw ICMP packet, which we have right here, and it doesn't seem to be that big. So it's a struct as raw ICMP. We take the buff, the address of the buffer, and we add the size of the raw ICMP, of the raw IP. Well, that's right too, and that should only be 20 bytes. What if we were to remove this? What happens then? Huh, it compiled. All the errors disappeared. Coolio. All right, let's test this out. Received packet with malformed checksum. 9025. 9025. Let's don't do the checksum for now. Or at least temporarily remove this here. And now the other checksum fails. Okay, let's see what happens now. Okay, something happened. Let's see what's what. Okay, so here we sent the packet, and this is what we received. 32 bytes, kind 3, ID 81, source and destination. Well, the destination is correct, but source not so much. And the payload, kind echo reply, that is correct. But why do we have the same here? Let's see. The source is equal to the raw source, the destination, the raw destination. And where do we call the constructor? Here, source, destination. That's weird. It's weird that some of it seems to be okay, like the destination is the correct IP address. But the kind is type 3. Where does that even come from? Kind. Maybe that's correct though. What does it say when we send the first packet? Kind 3. Okay, so that's right. And there's 8 bytes of payload on the ping packet. And there's 8 bytes of payload on the received packet. So that all seems right. Everything seems pretty much right, besides the source IP address. Why is that the same as the destination? That's pretty weird. Well, at least we are closing in, right? We are pretty close to getting this to work, as you can see. Only some small details left to figure out, which we'll do after the break. So see you in a bit. All right, you guys, welcome back. I think I might have figured this out. Both the checksum and this problem that we had with the source and destination. So let's do like this, that we put these things back, and we are comparing the checksum to this FFFF. And if we go to the checksum function, that is generally the way to do it, to compare it to those f's. But usually you have one checksum function for creating a checksum and another one for verifying it. Because when you verify, you don't do this inverse operation here. So basically, at this point in the code, I think the result is FFFF. But when we do this, we flip all the 1 bits to zeros, which means that the result is going to be 0. So that is what we should check for, not the FFFF. So I have put back both of these checksums. Let's just verify that it doesn't work. Right, so this is the checksum. So let's see what happens if we let's see, received packet with malformed checksum. Right, so it's the IP packet that it complains about now. So instead of this line right here, we should have an if statement which just checks if csum is 0, like this. So if we do this instead, what happens then? Is it still the same, or is it the other one now? Let's see. No, this says ICMP. Annoying. I thought I had figured it all out. But let's add one thing here. We are currently only printing the checksum from the IP packet. It would be interesting to print, wait a second, if it's 0, we give an error. I meant the opposite, of course. 0 means that it's okay. So this is how we should do. I'm glad I didn't change anything else because I thought it didn't work. Nice! So now it fails at the ICMP instead. And now we can just do the same there. So instead of this right here, we just check that ICMP checksum is positive. And now it should all just work. And it does. Pretty nice. Alright, so let's dig into this problem right here. And I think I have the solution to that as well. Because I wrote this two-dotted function quite a long time ago, but I suspect that this does not use malloc to allocate the pointer it returns here. So basically, both of these function calls refer to the same place in memory, so to speak. So when we do this, we overwrite the first result. So what we should do instead is don't declare these as pointers, but let's say we have a source with size 16 and we have a destination of size 16. And why 16? Because if we have an IP address at the maximum length with 3 digits per group or per octet, so then we have 3 times 4, which is 12, and we have 1, 2, 3 dots, which makes it 15, and then we want to have the null terminator at the end, so 16 is perfect. Alright, so let's see here. Before we do this right here, let's zero out our source, and the size is 16, and let's do the same with the destination. And instead of just doing it like this, now we can let's do one more step, by the way. Let's create an int16 len for the length of the string. And maybe we should have a pointer too. I call this TMP for temporary. So let's say we set this TMP equal to dotted, and then we provide the raw source. Then we calculate the length of the string. So we set our len equal to string len of the character encoded. Or no, this is an int 8, I think. So we can just provide the TMP like this. So now we have the length. So now we can do a memory copy. So we copy into our source variable we copy from our TMP. Maybe we can just do this. And we can copy len bytes. And since this is not a string copy, this is a memory copy, so it does not add the null terminator. However, we have already zeroed out the whole thing, so it will have a null terminator. And when we have done all of this, we do the same once again, but this time we take the destination here. This is still TMP, and then we copy into the destination. So now we can remove these two lines, and we can treat those string arrays as we have done with the pointers before, because they will fall, what's the word for it? They will degenerate into pointers. So let's see. Let's clean this up. And let's do this. So that was a lot of errors. A lot of errors. Maybe we should not define it twice, huh? So let me see. Yes, this should be gone. It should be gone. Alright, we need to have a string length function. Let's write one real quick. It's quite simple. So let's say we have an int16 string len, and it takes an int 8 star as an argument. And let's go up here, int16 string len, and it takes an int 8 star, which is the source, let's say. We need to have a pointer, and we need to keep track of the length. So let's say we have an int16 n. We do a for loop where we set n to 0, we set p to source. We're gonna loop as long as p is not the null terminator. And at each iteration we're going to increase both n and p. And that's it. Then at the end of the loop, this n will contain the length. Something like this. Compiles. And will you look at that? Now we have the correct source. This is my other server, the one we are pinging, and it has this IP address as the source because this is a packet that we are receiving after we have sent ours. And the destination is this machine. So it all looks good, right? The checksum checks out, everything is fun and dandy. I want to change the show function a little bit though, because we do not show the details of the ping packet. So let's see, show ICMP. So we are printing it as hex. We don't need to do that. But if we have data and one more condition, if we have data and the packet, is it called kind, is equal to, let's see here, is equal to echo or echo reply. Maybe we can do this. If packet, so if we have data, then we do an if statement where we check if the packet kind is equal to echo, or if the packet kind is equal to echo reply. In that case, we have a ping packet and we want to print out some extra details from that body, so to speak. This stuff that we have right here. Okay, so let's see. We need to define a pointer for that. So it'll be a struct as ping. Let's call this ping pointer. So we set the ping pointer equal to it'll be packet data, right? And that data is an array. So I guess we should take its address like this. Alright, so now we should be able to print the ID and the seek from that packet. So let's say we have an ID. Let's print it like this. See, we have this, and then a tab, and then this, and then a new line. Okay, let's follow the same format. So this will be a new line, and then 2 spaces, and we provide the seek. Okay, so we need to, these are 16-bit values, so we need to take care of the endianness. And what we're going to provide is the ping pointer and its ID. And we're going to run the endian on the ping pointer seek as well. Something like this. Let's try that. Alright, the ID is this, and the seek is this. And it should vary, which it does. Nice. Very nice. Very, very nice. How do we decide the seek, though? I don't remember how we did that. So let's see, where do we create the ping packet? Here we calculate the size of it at least. Here we malloc. We set the ID, okay, to 5,000. And we set the seek to 1. Huh. That's a little bit weird. How can we get so large numbers back? What does TCP dump say? ID 5000 seek 1, ID 5000 seek 1. Okay, so it sent the right thing. We are printing it wrong though, so perhaps we shouldn't do this this endiness. Maybe it's already being done somewhere else. So let's see, show ICMP. So let's not do this endiness, but we take this ID at face value, but we need to cast it into an integer at least. Maybe that might be it actually, that we are not treating it as an unsigned. But let's see what it says. I think I was right here. Let's put back these endiness thingies. But let's cast this. Let's cast this thing like this. Maybe we need to do this manually. So let's say this is an unsigned int, a regular unsigned int. We can try that. Down, and we do unsigned int here as well, because it is obviously the correct value. We just need to present it in the correct way. Maybe we are getting the wrong data when we point this thing like we do now. That might be it. Let's see exactly what we have here. 8 bytes of payload. And if we look at this, 8 bytes, so this is 2 bytes. Now I see. We are pointing it to this data. Is that the problem? What did I do here? I set the ping pointer equal to the packet data. And what is packet? Well, that's an ICMP packet. It's this one. And this has a data, but this is a pointer. This is not an array. Okie dokes. Now it's starting to make sense. So, all right. Did I delete this? No. Unsigned int. I think this is right now. There we go. So the ID is 5000 and the seek is 1 for the first packet. Splendid. So now we can successfully send IP ICMP packets. We can receive them. We can interpret the results. Even the checksum calculations check out. So that's nice. So the next step is, well, it's adding some additional things so we can, for instance, type on the command line what we want to ping, and we also need to show it a little bit better than this, right? So we'll do all of that after the break. All right, welcome back, you guys. So currently we are doing a lot of the heavy lifting inside of our main function, and we still are gonna do some of it there, but I want to break out the things that has to do with sending an actual ping to its own function. So let's see here. All of this. What did I do now? Undo. So let's see. It's pretty much all of this, all the way down here. So we'll break this out, and let's just put it here. And let's say we have a new function which is called bool send ping or something. And what do we need? We need to have the addresses, right? So let's say we have an int32 source, int32 destination. The ID number, the ID number. We need to also provide. How did we do it here? We created a random. So let's say we have how big is it? In 16, right? So we have the ID, we have the sequence number, and I guess that's all we need. We do also need all of these variables. Almost. This one should remain. So let's paste it in here. Let's just temporarily do something like this. We'll have a bool ret. I want to try this out so I know that it still works. So I'll set the ret equal to our new function, send ping. What's the IP addresses? It's these, right? So the source is going to be the inet address of this string. I don't need to do this, so or actually it takes the, okay, it actually takes the strings as input, so let's do it like that instead. Int 8 star, int 8 star, and then we don't do the init address stuff. We will just say something like this, 10.1.2.5, and send it to 10.1.2.6. Let's say the ID is 500 and the seek is 5000. If ret, we can just print OK or something. Okay, what's now? Implicit declaration. Forgot to add the new function here. So we are having a bool send ping and an int 8 star, another int 8 star, int 16 and int 16. And R&D we don't have, right? So this R&D right here is actually the ID, I think. I think so. Makes pointer from into right. It should be a pointer here. So maybe we can do, nah, let's just do this. Main is normally a non-static function. Okay. Maybe we should close this as well. There we go. All right, let's try this out. And we get an OK back. That's good. The ID is 5000. The seek is 1 though, so we don't control that. Where does the seek come from? I never seem to figure that out. We are creating the body right here. Okay, that makes sense. Here we should provide the seek. Then here we should provide the ID. All right, now it works. That's good. Now that we have this function which does all the heavy lifting for us, we can just deal with the command line arguments and stuff like that. So let's say we have an int 8 for the destination, and I'm not sure if we need to specify a real source. I think we can just give all zeros and it will figure it out automatically. So I think that's what I'll do, so we don't have to worry about figuring out our own IP address, which can be a little bit difficult at times. And okay, so let's check if argc is less than 2. Then we'll say something like usage, name of program, destination IP, and we'll provide the argv, and return -1. Otherwise, we will set the destination equal to argv1, and we will cast this as an indate. Okay, so now we know the destination. We also need to keep track of the sequence numbers. So let's say we have an int 8 seek, and we can set seek equal to 1. Or we can do that in a for loop. So we'll set seek equal to 1, gonna loop as long as seek is less than 1, 2, 3, 4, 5, less than 6. And we'll increase seek. Let's add some message, and I want to mold this after how Cisco does this stuff. So let's log into Cisco router. And let's ping something. This right here. Type escape sequence to abort. We can change this to Control C. And not type, but press. We put in the new line. And it's not going to be 100 bytes. Let's see how big they were. I guess they are counting this right here. So 8 bytes. This we need to replace with the address. Timeout is 2 seconds. Sure, why not? And we will provide the char version of destination. Alright, that's good enough. And then in the loop, what we are going to do is we will set our return variable equal to send ping. We are going to provide, let's try the all zeros, I think that will work. And the other one is our destination. Our ID is the, how did we do this? R&D is an int 16. Well, we'll just do this then. And here we set our seek. And by the way, this is a variable declaration, so let's put it in the right place. And now we have two different possibilities. Either ret is positive, which means it was successful. In that case, we want to print f an exclamation point. That means it was okay. Otherwise, we are going to print a dot. And we want to flush this so we can see it on the screen immediately. And afterwards, we would actually like to print something like this. Maybe we can, for the first version, we can make it a little bit simpler. So let's see, success rate is some percent, and we have this and this. Round trip, I don't want to have round trip calculations at this point. We'll do it in the later version though. So this is fine. Okay, so we need to calculate the percent, and we need to know how many we sent and how many we received. So let's see here. We can have an int 8%. We don't have to worry about any decimals. And we need to count how many were successful. So when we run this loop, we will initialize success to 0. And if it is successful, we can increase that. And the percent can easily be calculated by taking percent equal to the success divided by, let's see, divided by seek, and then we want to times this by 100 so we get the right thing. Maybe we can do something like, I don't know if this is possible, but it should be, I guess. So we say that this expression is a double temporarily. We convert success to a double. We convert seek to a double. We divide them, and this is to a double. Then we times it by 100, and when we have it in percent, we can go back to int 8, like this. I'm not sure if this works, but I don't see why it shouldn't. Alright, so now we can give the arguments here. The first one is the percent. Second one is the success. And the third is just seek. Like so. Yeah. Let's see what it says. Huh, compiled without anything. That's pretty nice. Okay, so we give this the 10.1.2.6. It only ran one, or maybe it didn't. Success rate 83%. It seems that our double stuff worked, but we did the wrong calculations, a little bit at least. Because seek will be 6 when this loop ends. So let's minus this first. And there's a lot of noise from the other functions. So let's find all the printfs. Okay, it's inside the show functions. Let's check the calls to show. Okay, this we don't need. So let's remove this and this. And here we have some error stuff. And this we don't need to print. Okay, I think that's it. $500. Okay. It's set but not used. 532. So it's here. Let's put this back. And let's only print something if it fails, right? Or no, we don't want to do that either, actually. However, if it fails, we want to return an error. Maybe we can unallocate this first. Just return false here. Yeah, something like this. It still prints all this crap. Where else do we have a call to the show function? This is inside of another show function, so that's not it. Show reply. Let's just remove this. Almost perfect. We need to add a new line as well. Is there any additional new lines we need? No, there's no here. So let's see. So, well, we can add it here actually. Look at that, 100%. By the way, what happens if we try to ping something which is not gonna respond? That's a little bit disappointing. Pretty weird, actually. So where do we have this reply thing? Here. Let's put this back. Show reply. And let's see what we get. Okay, so these are the packets that we get back. This is not the IP I tried to ping. Where does it get this from? Oh, didn't I change this thing? This should obviously be the source and the destination. Okay, maybe this does work after all. Let's start with something that does respond. Let's remove those. So this should be able to respond, and it does. This should not respond. Okay, now we're talking. Receive IP, return an error. We should not print that actually. Reply. Just return false. Same here, false. This is a more serious error, so here we can actually print it. Here we should also return false. Alright, let's try it. Unknown packet received. If we receive an unknown packet, we wanna recurse, because we want to check for the next packet in that case. So let's just return receive IP with our S. We do not need to print this thing. Okay, let's see what happens. As I suspected, the timeout is very big. Very, very big. So how do we change that? There is probably some socket option. Linux socket option set timeout. Receive timeout SO send time socket option to set timeout for any socket operations. That's nice. Struct timeout. That's really cool. Okay, so we can do that in our setup function. So let's set our what's it called? It's just called sec or so the number of seconds, let's say we have a constant dealing with that. So let's say we call it timeout like this, and the microseconds we can set to 0. So let's see, first we initialize the socket, then we set this socket option. We don't actually need to abort everything just because this fails. So let's remove this. No, we can't do that. But we don't need to do this or this. So now we can just do all 3 socket options. So what was the other ones? Receive timeout and send timeout. And these we call TV sec and use. Okay, I think I got it all. So this is this. And we have this, and this is not sol IP but sol socket. And we need to provide our argument, which is not an int. And we call them TV. Size of struct time val. So, and what was this called? TV sec and TVU sec. I think it was that. Sol socket, and we do this. Size TV. I think I got it all. No, I don't want to copy paste more than I really have to. We need to define that constant though. So one set but not used. Oh, that's right. I accidentally removed that part as well. Shouldn't have done that. This should be in 32.1. So unsigned int star. This should be the size of 32, I guess. All right, let's see what it says. Ha! Now it times out after 2 seconds. Isn't that great? Success rate is 0. And if we ping our .6, why would that stop working? Is this still responsive? Yes, it is. Why does that fail? What if we were to do stray/f, we put all this to this, and we grep for sock option. Protocol not available. Protocol not available. And if we run the regular ping the same way, why does it show so much stuff? Oh. So here we have Sol IP. Oh, I changed all of them. This should still be Sol IP. Whew. Maybe it still works after all. Fingers crossed. Alright, let's start by pinging the thing that does not work, does not respond. Alright, that seems to be working like before. And what about the thing that should respond? Ah, would you look at that, ladies and gentlemen? It works. It all works. Every little thing works. Isn't it beautiful? Beautiful. So let me just add one little teeny weeny thing. Timeout is this seconds instead, and then we can provide the timeout like this. Shouldn't change anything, but it's better this way. Now we can actually modify the header file if we want to increase or decrease the timeout. Alright, you guys, we have successfully created ping from scratch. And we have made it in a nice enough way that we can turn this into a library and use it to deal with all kinds of IP operations. Maybe add Ethernet and ARP and stuff like that. But I hope you have liked this entire series, and especially this episode, which I think is one of my better ones actually. I hope you do too, and that you want to like and subscribe and hype the new feature. Don't forget to hype. And please tell me what you thought about what you thought of the new intro or the intro sequence. Tell in the comments below. Thanks for watching, you guys, and thanks for tonight.